they say that if you cannot refute something, it may as well be plausible. So I know there are people here who find dark sector interactions to be exciting, and I also know there are people here who find that it's absolutely ridiculous. And that's absolutely fine. I'm not here to convince everyone that this exists or this is very interesting. What I want to do is to shed light on why people look at these interactions and what does the latest data have to say about these models. So I'll be sharing that, and I'll also try to share what we did in our recent papers that have been published in MNRAS on this topic. Right, so the advantage of speaking late in the day is that I can skip over the basics. So I'll skip over the basics and I'll go to this point, where if you remember the previous graphic, it's remarkable that you can describe it with just 6 parameters of the lambda CDM model. And the lambda CDM model is very good. It can explain almost all the observations that we have. It's only when you look very, very closely, when you try to compare precision data sets, that you find tensions. So I'm sure many of you, most here are cosmologists, but even those who aren't, I'm sure you've heard of the Hubble tension and other anomalies that are very, very significant in today's study of cosmology. So when you look at those and you wonder, well, then where is the issue? There can be issues in 2 possible regions. One, maybe there's some problem in some data set. Or maybe the lambda CDM model is incomplete. Maybe we need to tweak it. Now, I don't want to disappoint observers today, so we'll go with the second approach. Now, there are thousands and thousands of beyond lambda CDM models in the literature, but today I'll focus on a special class, on a special family of models, and this class has to do with interactions between the dark energy sector and the dark matter sector. But your question might be, why this particular family all of a sudden? Well, 2 very quick reasons. One, this family has shown some promise in easing the Hubble tension. Many authors have worked on this. And also, there is no fundamental reason why this cannot happen. So why not explore, since we are questioning the lambda CDM model. So this study was basically an investigation into the concept, the prospects of interacting models in light of latest data sets and in the context of cosmological tensions. So how do we go about doing this? A lot of equations. But no need to panic, it's very, very simple. What we are doing is a purely phenomenological approach. No Lagrangian, no fundamental theory. What we are doing is we are taking the plane or continuity equations and we are using sort of a source term to signify this interaction. And in this study, we choose a very special form, which is proportional to the density of dark energy. Now this is not theoretically motivated, we only choose this form because this has been shown again by other authors that is kind of helpful in the context of tensions. And then we do the full perturbation analysis, we implement these equations in Boltzmann solvers, do NCMC with the latest set of data. So the data sets that we took were CMD from plant 2018. We took supernovae data from the Panttheon Plus compilation, and we took SDSS BAO. So SDSS, because at the time we were working on this, DESI was not out, but we have updated the results with DESI. I'll come back to that towards the end. And it's not that we are the first ones to be working with these models. There have been multiple studies on this, but our analysis has a few key differences. So to begin with, in most previous studies, what people used to do is they considered dark energy equation of state to either be lambda or fix it to some value. So let's say WCDM models. We wanted to see what would happen if we consider some dynamical forms of this equation of state. So we considered 5 different cases, including lambda CDM and WCDM, and something called modified emergent dark energy, the CPA parameterization, KBQ parameterization. This is just to find out if there are any generic trends that we can find out from this analysis. Also, if I go back to the perturbation equations, you'll see there are terms which have 1 plus W in the denominator. What this means is, if there's a Franklin crossing, as Professor Koshuka was referring in the morning, these equations can go up. So what people do is they divide the parameter space into 2 parts, phantom and non-phantom. So we do the same. And experts here would know that certain combinations of Q and W lead to certain instabilities in these interacting models. So again, in the past people used to put hard bounds on these on these parameters before running NCMC chains. Otherwise, the codes may tend to fail. Here we thought, well, if the codes want to fail, let them fail. So we kept it completely open, and very, I won't say interestingly, rather unsurprisingly, we got parameter bounds which kind of respect those, those stability bounds. So it's just that we didn't want to put any theoretical priors beforehand and wanted the data to tell us what is happening. So right after all that, we also took the full effect of the dark energy perturbation, so we did the full perturbation calculations here. So what do we get at the end of the day? Okay, a very busy slide, and of course you can't read this, but the main thing that we found was for dynamical dark energy, in the phantom regime, there is a reduction in the correlation between H0 and sigma 8, which is otherwise present if you don't have interactions for, let's say, CPL or JDT. Here, that correlation tends to decrease. Not only that, you have this parameter Q, right? Q does not have any correlation with H0, which means whatever be the value of Q, H0 will not change given the data set. But it has a negative correlation with sigma 8. So if Q increases, sigma 8 will go down. Am I saying that correctly? Yeah. So this model has a capability to ease the clustering tension without, if Q, I'm making a confusion here, it's probably, I'm messing up the signs, but the main point is it tends to not change H0, but it will change sigma 8. And the fun part is in the phantom regime, Q has a positive sign. So if Q has a positive sign, that means there's a kind of an energy transfer from dark energy to dark matter. And due to this correlation, if Q is positive, Q increases, so sigma 8 goes down. So there's kind of a easing of the clustering tension. So that's the main result. Like when you open up dynamical dark energy, in this scenario, H0 is not affected, but in the phantom regime, sigma 8 tension tends to be relaxed. So that's probably the main result. But we also wanted to, these are the contour plots from where we found out those correlations. All that is in the paper. Yeah, so that was the main result, but we also wanted to see if certain extensions of this slide. So the first thing we wanted to see was, can we constrain the sound speed of dark energy perturbations using this set of data? We saw we can't, you don't get any constraint with this set of data, like say we, and BAO. And we also wanted to see, well, is it possible for dark matter to be warm? So we also opened up the equation of state of dark matter WDM, but also that is very strongly constrained to zero. So no signature of warm dark matter, at least in this scenario, in this very special scenario. We also wanted to see if there is any effect of adding redshift space distortion data. Now, what happened was, we found the constraints got very tight for most of the parameters, also Q. But for some reason, the clustering tension solving capability of these models decreased when we added RST data. So we think this is probably because there's some sort of a lambda CDM bias in the way RST data is extracted. So that is something that we're currently re-evaluating, and whether we can do it for the models that we are using this for. So that's something that's under progress. And then the most important, interesting thing, again, Dr. told us about DESI. So we wanted to see, when we used SDSS and DR16, what would happen with DESI DR2. So the main result stays the same, that in the phantom regime, H0 is not worsened, clustering tension is reduced. But of course, since it's DESI, you have higher precision, so you get better precision on almost all the cosmological parameters. And DESI DESI is making news because of the equation of state. So we wanted to see how it evolves. But of course, we cannot make a direct comparison, because remember, we are making a very distinct difference between the phantom and non-phantom regimes. But DESI keeps it open, so you see the phantom crossing. We are currently working on a method to handle this phantom crossing elegantly in interacting scenarios. Only then we'll be able to directly compare with DESI results and comment on how these interactions and the tension solving capabilities work with this new data set. So that's also something we are currently working on. So yeah, sorry, how much time do I have? Perfect. 1 minute only. Perfect. Thank you. So this is summary. The summary is, of course, interacting models are not the only models that can solve tensions. But we wanted to study what is the status of this in light of various data sets. And they seem kind of promising, but of course, more investigation is required. required. Like you can use other interaction terms, or you can use other combinations of data sets and stuff like that. So that's something that needs to be studied. Second point that I want to make is precision data is very important in these contexts. Thank you. In these contexts, so DESI does make a difference, and we are expecting that future data releases will be much more helpful. Of course, this thing that phantom crossing needs to be handled carefully in these interacting scenarios. So that's something we are working on. And if you are interested in that, please come talk to me. And of course, this is something that I like to say at the end of all my presentations, and that is that cosmological tensions are bad because this means that we don't understand our universe very well, but it's also it makes the subject very interesting. Of course, it helps us keep our jobs, but it also raises questions which ultimately lead to discovery, and that's something that is very, very exciting to me, and I'm sure to everyone. So if I have another minute, I just want to share what else I work on usually. So my usual research is on cosmological tensions and anomalies, and I like to do this using novel statistical and computational techniques. So let's say subjecting beyond lambda CDM models with latest data sets, such as an example that I showed you today. I also do simulations and forecasting with future missions, and I'm also interested in machine learning to non-parametrically reconstruct the late-time universe. So in fact, we also developed a deep learning package called Ladder, which can reconstruct the late-time universe using coordinated supernovae data.